Hello my dear students, welcome to my YouTube channel. Myself Dr. Sohail. I am a PhD in Chemical Engineering from the Indian Institute of Technology, Roorkee. So if you are new here on this YouTube channel, please consider subscribing. Also press the bell icon for future notifications. So in my last video lecture, we have discussed basic modes of heat transfer. I will be providing the link in the description box. So in this lecture today, we will be discussing heat conduction through a composed wall. So here you can see we have a composed wall made up of three different materials. Three different layers are there: layer 1, layer 2 and layer 3, and they have different thickness L1, L2 and L3, and they are different materials, so their thermal conductivities are also different, K1, K2 and K3. And these are the outside temperatures T1 and T2, and these are the interface temperatures between the layers. So if we consider this system, for this system we consider that these thermal conductivities are independent of the temperature, so the heat transfer through these layers can be considered using the Fourier's law, which we have discussed in our previous lecture. So Fourier's law, if we can write it for layer 1, we can write the Fourier's law as Q is equal to K1 A, and difference of temperature will be T1 minus T prime, T1 minus T prime by L1. Or if we can just rearrange it, so we can write it like T1 minus T dash is equal to Q L1 by K1 A. Let's call this equation 1. And similarly we can write for layer 2, Q will be equal to K2 A T dash minus T double dash divided by L2. So rearranging this, so we can come like T dash minus T double dash is equal to Q L2 by K2A. Let's call this equation 2. And similarly for layer 3, we can write Q is equal to K3A, it will be T double prime minus T2 by L3. Again rearranging this equation, it will be T double prime minus T2 is equal to Q L3 by K3A. Now what we can do is that we can add equations first, second and third. What we will get is, we will get T1 minus T2 is equal to Q, we can take common, and we can write L1 by K1A plus L2 by K2A plus L3 by K3A. So is that it can be rearranged like this. We can write Q is equal to T1 minus T2 divided by L1 by K1A plus L2 by K2A plus L3 by K3A. So this is basically, this T1 minus T2 is the overall temperature difference. And this is basically the total thermal resistance that's offered by this composed wall. Total thermal resistance. So this is basically your thermal resistance. We can say it's R1, this will be R2, R3. Resistance by layer 1, resistance by layer 2, resistance by layer 3. Basically total thermal resistance will be RT will be R1 plus R2 plus R3, or it will be L1 by K1A plus L2 by K2A plus L3 by K3A. So what it basically says is that the total thermal resistance, it states that total thermal resistance is additive in as the electrical resistance in case of series. So as you can, in the case of electrical resistance in series, the electrical resistance are additive. Similarly, the thermal resistances are additive in the case of this composite wall. So if we have more layers, so we can just add the thermal resistances. So this was about this solid composite wall. So in my previous lecture, actually in the previous video lecture, I have given one problem related to the Fourier's law of heat conduction. So we will try to work out that problem here. So the problem goes like this. We have a solid wall. This is a solid wall. So we have the temperatures given. T1 is equal to 1400 degrees Celsius and T2 is equal to 150 degrees Celsius. Sorry, degree Kelvin. It's degree Kelvin. And the thickness of the wall is basically 0.15 meter. And we have given the thermal conductivity is 1.7 watt per meter per Kelvin. So in this case, we have, if we can write T1 is equal to 1400 degree Kelvin and T2 has been given as 150 degree Kelvin and L is equal to 0.15 meter and your K, thermal conductivity, is 1.7 watt per meter per Kelvin. So what we can do here is we can use the Fourier's law of heat conduction, that's Ka T1 minus T2 divided by L. Now we have this, since A is not given, so we will take it per meter square. So we will just take it like Q by A, that's it will be per meter square, rate of heat transfer per meter square. So K is given, T1 and T2. So here in this problem we have K is given and T1 and T2 are given and L is also given, that is the heat flow path. So in this problem we have to determine the heat flow through a wall, heat loss through 0.5 meter by 3.5 meter wall. We have to find this. So we can first find Q, that's heat per unit area. Its K is given, it is 1.7 multiplied by, we have T1 is given 1400 minus T2 is 150 and then we have L is given 0.15 meter. So it will come out to be 2833.33 watt per meter square. Since it's per meter square, so then we have to find heat loss through 0.5 by 3.5 meter wall. So it will be equal to 2833.33 watt per meter square multiplied by this area 0.5 into 3.5 meter square, and meter square will cancel out. So you can just multiply these and here you will get 4250 watts. So this is the answer. So you can also try several problems related to this concept of Fourier's law of heat conduction at your places, and in the next video lecture we will also try to solve some problems related to the heat conduction through a composite wall. So I hope this is enough for today. So I would in the end also I would request you all to subscribe to my YouTube channel, and please share this video also with your friends. In these times of COVID-19 pandemic, I would also request you to please stay safe and stay home. Thank you.